Okay, so we're determining whether carbon tetrachloride is polar or nonpolar. We're naming all the structures and drawings. We're going to make a claim and we're going to justify the claim. So we started out with the electron dot formulas, each of the elements shown here, atoms shown here with the electron dots that we get for that. Those are the electron dot formulas. They come from the valence electrons we determined from the periodic table. We share the electrons to get each of the atoms to have the number of electrons they'd like to have to be as stable as possible, and then from those electron dot formulas we get the sharing arrangement. Now we're going to draw a Lewis dot formula where we squeeze the electrons that are shared, these four sets. That's a set, that's a set, and that's a set, and that's a set. We're squeezing those four sets in between the atoms that they're shared between, and we're going to finish putting the electron dots around this. So each of the chlorines have 3 lone pairs in addition to the shared pairs they now have with carbon. So this is the Lewis dot formula. From the Lewis dot formula, we're going to find the electron the electron pair shape. And we have 4 sets of electrons around this central atom. Here's a set, here's a set, here's a set, here's a set. You can have sets of 2, 4, or 6. These just all happen to be sets of 2. And when you have 4 sets of electrons around a central atom, you get a tetrahedral arrangement. Okay, so that's a tetrahedral. And you don't have to circle the dots, by the way, the shared dots. I just do that to make sure we're clear on what I'm talking about as far as where those shared pairs are located. Okay, from that tetrahedral electron pair shape then, we're going to replace any pairs of electrons that are shared with the atom symbol that belong there. In this case, all 4 sets are shared. So we're going to replace all 4 sets of electrons on all 4 of these arms with the element symbol for chlorine. And since we don't have any lone pairs left, this is the molecular shape. It's still a tetrahedral arrangement. Okay. So, I could stop right here as far as being able to determine whether it's a polar molecule. And here's why. To have a polar molecule, you've got to meet 2 conditions. Okay? You have to have both an uneven arrangement and polar bonds. If I don't have both, I can't have a polar molecule. I didn't remove any electron pairs, so this is going to be an even arrangement, not an uneven arrangement. Does that make sense? So my claim here is that carbon tetrachloride is non-polar. My justification is to be polar, a molecule must have polar bonds and an uneven arrangement since no lone pairs of electrons were removed, there is no uneven arrangement. Okay? How did everybody do?
So you can need a tetrahedral bent shape, whatever.
There is no bent shape. There's no modified electron pair shape because we didn't have any lone pairs back here on the Lewis dot formula. Not on the central atom anyway. The central atom only had shared pairs, so there's not going to be a modified electron pair shape. When you have a modified electron pair shape, when you replace the electrons, the dots, the pairs of dots here, with the element symbols when those electrons are shared, and you have a pair of electrons left over without an element symbol on there. Okay? So that would be a modified electron pair shape. We don't need one here. We don't have one here. And if we don't have a modified electron pair shape, we can't have a polar molecule. Because you have to remove a lone pair of electrons to get that uneven shape of a molecule. At least in this really super simple, almost simplified to the point of absurdity method we're using. Okay? There actually is a way to have a tetrahedral arrangement of a molecular shape and still have a polar molecule. We just haven't done any in here. Okay? We're really working with really simple stuff right now. Okay? You with me? All right, just so I don't leave you in the dark, the way that you can have an even arrangement of molecule and still have a polar molecule is if you have some of the atoms are different out here. So some of the outlying atoms are not the same, and you have an extreme difference in electronegativity between some of those. Huh? That would be the justification for this. That'd be incorrect. That would be, a false justification because you don't have that. Yeah, you can justify that. There are. That's why I'm saying. Part of the reason why I'm saying we're really super simplifying this methodology right now. Okay, just to get you guys kind of started thinking about how it works. Yeah.
Can anybody be good enough like just look at like the first ones, like one of the first ones and like know? Not off memory.
Yeah, I mean after you do it a while, I could probably look at the formula and sort of go through the whole process in my head and figure out whether it's likely to be polar or not. Yeah, I mean once you and after a while carbons have 4 dots, chlorines have 7. You put it all together, by where they are on the periodic table whether they are going to be polar or not in general, because up here in the corner we've got a really extremely large electronegativity, and I know that as I go more in this direction, it becomes less and less. And I know about how much difference there is here. So I can make a really good estimation whether it's a polar molecule or not just by knowing where the atoms are on the periodic table without even memorizing electronegativity. Just knowing that the electronegativity of fluorine is about 4. Okay? The electronegativity of hydrogen is about 2. Things like that. I can make a really good estimation of whether I have a polar molecule or not, whether it's going to behave in a polar manner. Okay? And when you get into larger molecules like those organic molecules, okay, then you've got other things that go on that affect polarity too. So that's something that you can get to if you're going to go into medicine, or if you're going to go into nursing, or you're going to be a pharmacist, or you're going to be what's the word? Working with animals, veterinarian. For some reason that escaped me at the moment. Okay, you're going to need to know all this stuff. Okay, all right.